Okay, here's a question on electromagnetic induction from November 2017. It's the matric paper. It says the diagram below shows different positions A, B, C, D, A of the coil in a DC generator for a complete revolution. The coil is rotated clockwise at a constant speed in a uniform magnetic field. The direction of the magnetic field is shown in the diagram below. So here is the direction of the magnetic field. It is going this way. So we have a whole lot of field lines all going in this direction. And then the coil here, you can see, is turning this way. So vertical, horizontal, vertical. But you can see that this side of the coil was on top, and now at position C, this side of the coil is on the bottom. Okay, and then in a full revolution, the top dark side of the coil has come back to its position where it started from. So it's a full 360-degree revolution. So here is 0, here is 90 degrees, 180, 270, 360, one full revolution. Okay. Write down the energy conversion that takes place during the operation of a DC generator. Well, every generator, the point of generating is to generate electricity. So it is going to give you electrical energy. How did it make the electrical energy? It used mechanical energy or kinetic energy, but it's more correctly like mechanical energy. So we're going from mechanical energy to electrical energy. Now it says, sketch a graph to show how the induced EMF of the generator varies with time. Clearly indicate positions A, B, C, D, and A on the graph. So we're drawing a voltage graph, okay, against time. So when we draw this graph, we need to think about, are we drawing a sine curve, or are we drawing that set of little hills? And this is, look here, DC. So DC, we don't need the sine curve, so I can put the x-axis on the bottom. And then I need position A, B, C, D, and A, because it says clearly mark them. Okay, so what does Faraday's law of electromagnetic induction talk about? It talks about the flux linkage. And how can we increase flux linkage? We increase flux linkage when we cut through more lines when the coil cuts through more magnetic field lines. But as you can see in position A over here, the field line is actually parallel to the coil. So there's actually going to be no EMF. And where will we cut the most field lines? We will cut the most field lines as the coil comes down to this position B over there, because we will be just swiping through all of the field lines. So the current will be at, the voltage, will be at a maximum in position B. And then as it turns back to position C, you can see at position C, can you see it is once again parallel with the field lines? It's not cutting them. So voltage is at a minimum. As it comes up to position D over here, it's once again flat, and it's parallel with the it's once again flat, and it's perpendicular, not parallel, it's perpendicular to the field line, so it's cutting as many as possible. So it'll come up to another maximum, and then when it returns to position A, it's not cutting the lines anymore, and it'll go to a minimum. And this is a full rotation. So just make your curve more nice and curvy than mine. It's hard with this pen to make it nice and curvy, but you need two domed hills, 90 degrees, 180, 270, 360. Now it says to you here, 10.2, a small AC, we forgot to label this, time, sorry. A small AC generator providing an RMS voltage of 25 volts is connected across a device with a resistance of 20 ohms. The wires connecting to the generator to the device have a total resistance of half an ohm. So this is unusual, because normally we get the thing saying ignore the resistance of the wires, or the wires have a negligible resistance. Now they are telling you they have a resistance. So in actual fact, we can look at these wires as being a series resistor in series with the 20 ohm device. So the total resistance of the circuit, it says here, write down the total resistance of the circuit. It's going to be your 20 ohms for the device and your half an ohm for the wire. So your total resistance is 20,5 ohms. Now it says calculate the average power delivered to the device. And they said to you, VRMS there in the question is 25 volts. So I looked at this and I was like, 5 marks? Where do they get 5 marks from? And you just plug voltage into the power formula. But what you have to realize is that this is a series circuit, and in a series circuit is a potential divider. So these wires have a voltage. The whole resistance of the wires will have a voltage, and the 20 ohm device will have another voltage over it. Because the only thing that is the same everywhere in a series circuit is the current. So in actual fact, if you go, and we can use this, average power equals volts squared over resistance, and because it's an AC circuit, it's volts RMS squared. We can take the RMS voltage of 25, okay, and square it and put it over the resistance of the total circuit, 20,5, and we will end up with this AC supply providing an average power of 30,49 watts. But it is providing this average power to both the device and the connecting wires. So in order to find out how much of this power is used on the device and how much is used on the wires, we actually have to find the current. And once we've found the current, we can then figure out how much power is lost in the wires. So if we want the RMS current, okay, we can work out the RMS current using the RMS voltage. So this is the Ohm's law formula over the resistance, okay. So it's basically Ohm's law but in AC, so we use RMS. So we've got 25 volts RMS according to the question, and we've got a total resistance of 20,5 ohms when we add the device and the wires. So the current, which is the same everywhere in the circuit, is 1,22 amps. Okay, so this average power is the power for the whole circuit. So if we want to calculate the power for the device, we can then go and subtract the power for the wires from the total power. So P total, okay, is going to be P of the wires plus P of the device. So P total we knew was 30,49, and we want P device, so let's calculate P wires. So P wires, we're going to use this RMS current because it's for the whole circuit, because current is the same everywhere in a series circuit. So the power in the wires is going to be I squared R, okay, remembering that this is I squared RMS. We should write it in there because we're using an AC circuit, so always try to remember to write in the RMS subscript, because otherwise they might think you've got a DC circuit even if in your brain you know it's an AC circuit. So I squared R for the wires is a half an ohm because it's there in the question. So this is 0,74 watts. So 30,49 is going to be equal to 0,74 plus P device. So if we take that away from 30,49, you get the power on the device is equal to 29,75 watts. Okay, so that will be your final answer, and that's why this is 5 marks. It's not just 3 marks when you could come over here, because this wattage that you found in step 1 is the power for the whole circuit. And so remember, your power is going to be split up between your two resistors, the resistor being the device and the wires.